We can start again. So for the second talk of today, we have Alireza, who's a postdoc at UC Berkeley under the supervision of Michael Jordan, and who is gonna talk a bit about data markets from data monetization to platform architecture.
Uh, Thank you, Antonio. So today I'm going to talk a little bit about two of my works around data markets and privacy. One is the work with Mike, the first one, and I will, towards the end of the talk, I will talk a little bit about the work from my PhD around the same area. Uh, and when I talk about data markets and privacy, the way that I usually think about it is that, any machine learning paper that you open, it starts with we have a data set, but then the question is where does this data come from, right? And the typical answer is that it's the user's data. But users have incentives in sharing their data. They might have some reservations in sharing their data, and a big factor shaping these reservations or concerns has been privacy. And there have been lots of surveys documenting, the growing concern of privacy here in US. So in 2021 showed that 86% of US population have a growing concern about the privacy of their personal data. And so all in all, this has led to researchers in academia and even tech companies from Apple and Google to Uber and Microsoft start thinking about redesigning their algorithms or models to incorporate certain privacy constraints. But it's not an easy task. There is an inherent trade-off here. If you want to offer privacy, in some sense, it's going to impact how much you can learn from data. And so some are saying that, what we have in US is not good enough because, it's not offering the privacy that it should be there to protect the consumers and users. While others are saying where we have stronger privacy guarantees, such as the GDPR in Europe, there are downsides of it, and with that, it's hurting innovation. It's disproportionately impacting smaller firms. I'm going to talk about it a little bit in the middle of the talk. But what I'm trying to say is that it's not really an easy question where you should stand. It's a trade-off between learning from what you want to learn from data and, of course, the privacy concerns. And in this talk, I will go over two papers. The first one would be around data collection and data monetization. And the questions such as, how the privacy mechanisms offered by, platforms impact the user's welfare and the platform's decision of offering services and even entering the market. And the second part, I will take a step back and think about, the architectures of the data markets and data acquisition that can benefit the users. And in particular, we will ask what type of architectures are optimal from users' point of view. Of course, we would need to define what do we mean by optimal. And also the question of even if we consider such architectures, how strong privacy guarantees are, especially when you have a monopolist in action for the second part of it. So before I get started with, the first part, I should say that these two papers connect with a growing literature in terms of data markets, data acquisition. They come with different names from different literatures, and data collection across economics literature, operations management, operations research, and of course, computer science literature. And different papers take different approaches to these, to these problems, from, a mechanism design type of approach to, designing mechanisms for data sharing, to more to a descriptive type of approach would be the main focus of the talk, understanding how, markets operate, and to, questions from different other different aspects. And the list of papers here is by no means complete. I just tried to put a few from different literatures all across this, communities, to just highlight that people are really coming from different aspects, from economic aspect, operations and market aspect, and also from algorithmic design and computer science aspect, to think about different problems and the intersection of, learning from data and incentives, and also, concerns such as privacy and even fairness, which I haven't included here. So with this, let's say, introduction, let me get started with the first part of the talk, which would be around data monetization and first party. So the classical approach, the typical approach that has been there to follow users across the web and collect their data and observe their behavior has been through third-party tracking cookies. If you have iPhone, you might have noticed over the past, I would say, 5 years or so, you have received this notification that, ask app not to track, Or if you're using Google Chrome, you might have heard that Google is trying to soon limit, these third-party cookies. And so all of that has led to the rise of what is called first-party data in the landscape of collecting users' data. So what is first-party data? It simply is the data that companies collect from you because of offering you a service. One running example that you can think of throughout this talk is MasterCard. So MasterCard is issuing credit cards and helping you to do transactions. But at the same time, MasterCard gets to see your transaction history. And so now they have this huge data set of users' transaction history. And if you go to their website, they have this data and services division, and they're saying, hey, we have all this data. If you want to find high value consumers, in an intelligent way, so they have this intelligent targeting, you can find them throughout their data. So they have this different set. Like, are you looking for people who spend on, clothes? Are you looking for people who spend on food? So, they really have this data set and they make money out of it. And this is not really limited to MasterCard, especially in US, all these big retail companies, Walmart, Target, and others are starting to, leverage this first-party data and make money out of it. And so the question, and this is really a change in the last landscape of data collection. Now that third-party cookies are getting more and more limited, first-party data is like becoming the new replacement for, data collection and placing ads and everything like that. And if you think about it, you're really having a three-layer market. The first two layers are users and platforms, the typical, two layers that interact in many of these type of problems. But now you have a third layer, which is the data buyer or advertisement company. And so the way that this works, if you think about it, is that users go to these platforms to get their service. But because of getting that service, as a byproduct, platforms get to see your data. You go search something on Google, you get your response, Google gets to see your, data, your search inquiry, or MasterCard, the same. You get a transaction approved through MasterCard credit card, but at the same time, your transaction history is visible to MasterCard. Now, these platforms have this valuable data, as we talked about, so they put it for sale, and the data buyers come and pay for that and get this data of yours. So if you think about it, now data buyers has your data while really not interacting with you directly. You never interact with these data brokers directly necessarily in this way. You interact through these platforms, but they get to see your data. Now, the first question to better understand the dynamics of such a market is to try to put a model on it. So let me get started with the model, and then I will go through some of the results that we have. So here we assume we have a user, which we denote as data by theta, a d-dimensional vector that encapsulates all the feature vectors of the user. Let's say what type of food they like, what type of clothes they like, what type of movies they like, everything. I mean, I'm just giving an example. And this user is interacting with, let's say, K platforms. So this platform I has its own vector of attributes xi, which basically denotes what type of services that platform I offers. For instance, if it's a restaurant, xi has elements and the entries corresponding to food, and probably no element in the entries corresponding to movies or like clothes or something like that. And so if you're familiar with the recommendation system literature, the way that we capture the closeness of this theta user and platform xi is by looking the inner product, theta transpose xi. So now the platform observes a signal of this theta transpose xi, which is a noisy version of it. I mean, due to the maybe noise in the observation. And so this is determining basically the quality of the service, how good they can estimate the closeness of the service that they offer and the feature vector of the user. But that means that they have an information about your data. Of course, they have a data transpose xi, but that is some information about your data as a user. And so there is now a data buyer that wants to learn some other function of data. So we say data transpose y. So y now the attribute that the buyer is trying to learn. And so they go to these platforms. And so if platform I sells them in data, we will talk about when the data selling happens. If they sell the data, then they will sell it, we assume, with some noise sigma squared. So platform I sells the signal that they have or the data that they have plus some noise, which is variance is sigma I squared. And you can think of sigma I squared as the privacy mechanism offered by this platform to the user, right? So you can think of it as how much privacy platform is committing to offer before selling to the user, before selling the data to the buyer. And the buyer pays to the platform because of the data. So the way that this operates, going back to the three-layer market that we talked about, is that first the platforms decide whether they're going to enter the market or not. And if they do, they're going to decide on some privacy guarantee or noise variance that they're going to offer. Now, users observe all these platforms, their excise, their commitment to privacy, and decide whether they are going to work with any of them or not. So they end up working, let's say, they end up interacting with a subset of these platforms. So the ones that don't have data are out already because they don't offer a service to user. Now, those that have data can price their data for the data buyer. They're going to say, hey, I have this user data. This is the noise that I'm going to add. This is its price. Do you want to buy or not? And the data buyer can see all these offers and decide based on, their why and the prices and the quality of the data, how much noise has been added to it, to decide to buy a subset. So this is roughly the model. Before I go into, how we analyze it, I need to give you basically a quantification of whatever I've been talking about, how much we learn about all of this. And the way that we use simply is through this, revealed information function or information gain, which simply is, we measure how much after observing something, let's say, for instance, the signals that I talked about, how much I can reduce the uncertainty about the data or the variance of data before and after observing the data, and this is called reveal information or information gain, depending on which literature you're coming from. And really, think of it as the mean square error. Like, I have a mean square error of the optimal estimator before and after observing the signal, and I look at its reduction and name it reveal information. I will stick to this for the sake of this talk. Really, you can replace it by any function as long as it's submodular in terms of the data. The information is submodular. What do I mean by that is that having one more additional data has a diminishing marginal value. Now, let me give another piece of definition, which is about the utility functions, and then we will go to the result. So users reveal the information to platform I, as I talked about, is how much they can learn about this theta transpose xi, the similarity of the user's attribute vector and the platform. This is going to be I of I. And how much the buyer learns about your data is going to be theta transpose y, given the noisy signals that are the purchases of the data buyer about your data. Now, users utility is basically about how much platforms learn about your data, which is something that you want because it determines the quality of the service, minus how much that data buyer wants to learn about you, something that you don't like about, how much learns about you, that's something that you don't necessarily like it. And this alpha basically determines your privacy sensitivity. So if you don't care about your privacy at all, alpha would be 0 and you enjoy the service, really don't care about privacy. If you're a very privacy sensitive person, then if the data buyer learns something about you, that's gonna heavily impact your utility function. Platform's utility, on the other hand, depends on the quality of the service that they offer. If they offer better, they can expand their user base or, the subscription that they get, plus the money that they make out of the data, selling data, minus some cost of production. You can think of it as cost of entering and, offering some service. And finally, buyer's utility is how much they learn about the user's data times how much they care about it, beta, how much they are willing to, invest on user data minus the total amount of money that they pay for that data. So again, there are two parameters here. I will get back to them soon. One is alpha, which determines or denotes the user's privacy sensitivity, and the other one beta, which kind of, captures how much buyer cares about learning users' data after all. One last piece of definition is that about this cost of production, I say a platform. Yes, sorry, go ahead.
Yeah, sorry. Can you just repeat briefly what is P? Sorry, I
Oh, it's
lost
the
it.
payment. Is the payment by the buyer to the platform for buying the data.
Okay. Okay.
So the
Nice.
platform gets some money out of it. So it's a monetary payment, and then the buyer loses money basically for buying
Yeah,
that data.
okay. Okay. Thanks.
And one last piece of definition is that the platform is called to be low cost if its cost of production is below a threshold. This threshold, one half really coming from analysis, but really think of it as, as a threshold that we define, and it basically determines, whether platform needs to sell data to continue to operate, or even if they do not sell any data, the gain that they get from interacting with user and offering a service is enough for them to continue to operate. But really, this is a threshold. Now, the definition of equilibrium that we go, because it's a multi-stage game, is going to be sub-game perfect equilibrium, which simply says, the game runs in a couple of stages, from platforms deciding to entrance and in their privacy guarantee to, users sharing or not, to platforms setting the price, and then buyers. And so the way that we define the equilibrium, very informally, is that we start from the last stage, assuming everyone has taken the action, what is the best response of the buyer, which set of data they're going to buy, then the platform's pricing best response, knowing the buyers will play best response, and so on and so forth. So this is going to be the notion of equilibrium, sub-game perfect equilibrium. Now, the first result that we observe is that at equilibrium, either a platform does not enter the market, or if they enter the market, two things will follow. One, the user will share data with them. B, the price of their data would be the marginal value of their data. What does it mean is that they are going to price it at the value that makes, in some sense, the buyer indifferent between buying that additional data or not, right? So they're going to look, okay, what if I do not sell my data? This is going to be the utility of the buyer. If I sell my data to buyer, this is going to be their utility. What's the difference? This is going to be the price of my data. So the marginal value of their data is going to be their price, and the buyer will buy their data. So what does all of this mean? It means that to characterize the equilibrium of such a market, I need to decide which subset of the platforms will enter the market and what privacy guarantee or noise level they are going to choose. After I know that, the rest I know how will happen. Like the user will share with them, because if they don't, the platform has the incentive of, increasing their privacy guarantee to convince the user to share. And then if the buyer doesn't buy from them, they have the incentive of reducing the price. So we can show that anything outside of this, characterization cannot be an equilibrium. Now, let me give a little bit of an example through looking at a simple case with two platforms to see really how does it out. So suppose I have two platforms. So remember, platforms decide on the privacy guarantee that they offer. So suppose platform one offers sigma 1 squared as their level of noise. Platform 2 offers sigma 2 norm squared. Now, if sigma 1 and sigma 2 norm squared are high enough, it means that they're offering good privacy guarantee. Then the user will end up sharing with both of them. The user is like, okay, these guys are doing a good job in terms of privacy. I'm happy, I'm sharing my data. Now, on the other hand, if they offer a very low privacy guarantee, the user will not share with any of them. And if one platform does a good job, the other one doesn't, then the user will only share with the one that is doing a good job in terms of privacy. Now, what I claim is that, and one quick note is that this is for the case that user is privacy sensitive enough, because if they don't care about privacy at all, let's say that alpha is 0, then the red area will shrink and everything will shrink to blue, right? If I don't care about privacy, regardless of what privacy you offer, I'm going to always share to get the service. So we are looking into some, let's say, non-degenerate case where the users have some level of, privacy concern. Yes.
Sorry, just one more stupid question. How do users understand how much data is shared?
Could you say it one more time?
How much, like, do the users understand how much of their data is shared?
With the buyer, yes. So because the platforms publicly say that commit to, how much noise they are going to add. Right.
Okay.
So
So
it's like,
this is public. Okay. Something.
yes,
Okay.
yes,
I was okay.
yes.
Thanks.
So now what I claim is that the equilibrium really falls here, the intersection of these two regions that user shares with both of them and not shares with both of them. Why is that? Let's look at it. Suppose the equilibrium is somewhere in the red region, right? The user doesn't share with anyone. Now, platform one looks and says, okay, maybe I can increase my privacy guarantee, do a better job in terms of privacy, go to the yellow region. Now, at least user will share with me because I'm doing a good job in terms of privacy. But if they go there, the same argument holds for the other one. Like the other one is like, okay, I can also increase my privacy guarantee and get the user's data. But if they are in any of these two regions, now there is still one platform that is not getting data, and they were like, hey, like here, if you're in the green region, platform one is not getting data. Platform one will be like, hey, I can increase also my privacy and go to the border, right? And now I will also get data. So you can see that if one of the two platforms is not getting data, they have an incentive to offer a better privacy guarantee to come back in some sense to the game. Now, if they are both getting data, but they are not at the border, it means that in some sense they are offering too much privacy. Now, platform two here in this example will be like, okay, maybe we are offering too much privacy. The user was willing to share with the lower privacy. So I take down my privacy. It's still, in the blue region, still data is shared, but at the lower privacy means that I can get more money out of the user data. And so with these sort of games, you can show that the equilibrium will fall at this point, which as a consequence means that when user is privacy sensitive enough, their utility will be zero because they will be at the intersection of, not sharing and sharing their data. Now, this was a simple case in the two platform case. Does this hold in the general setting? So there is following result that I'm going to show you characterizes the equilibrium in the most general setting and show that in fact this is quite general. So remember, beta determines the buyer utility's dependence on learning users' data, right? I'm a data buyer. How much I care about learning users' data, that's this factor beta. If beta is above a certain threshold, we show that at equilibrium, all platforms enter the market and the buyer purchases all platforms' data. If beta is lower than a certain threshold, we show that only low-cost platforms enter the market. Kind of makes sense, right? If the buyer is not that much in need of users' data, they are not going to pay that much. So only the platforms that can still operate with the user service are going to continue to operate. The rest are not going to enter the market. Now, going back to what I just told you, in both cases, the user utility could be as low as zero, depending on their privacy sensitivity, but the buyer's utility is strictly positive. So there is a huge contrast between user and buyer, despite the fact that in some sense, it looks like competition should have benefited both of them. You have competition between K platforms, but the user utility could dramatically go down as they are more privacy sensitive. But buyer utility is still always positive given the competition. Now, why is that? Why the competition doesn't help the user? I mean, it's intuitive competition help the buyer, right? The buyer, okay, they have more ways of buying the data. So the price of each platform's data is going to be lower because the marginal value of each data is lower. So that makes sense. One would expect that probably the competition should have helped the user as well. But the point is, although the competition helps the user, but competition was helping the buyer as well. But that indirectly hurts the user. So think of it this way. I'm a user. There are many platforms out there. I'm benefiting from their competition. But many platforms out there means that for an advertisement company, there are more ways of reaching out to my data, right? Now, my data is on Twitter. My data is on Facebook. My data is on MasterCard. My data is on, all these websites, Google. When there are more ways of getting to my data, this model is telling me that that could hurt my utility because getting my data becomes easier and easier for that data buyer. And the combination of these two effects could heavily reduce the utility of the user if they are privacy sensitive. So competition at the first glance looks something that should help the user, but it's not necessarily the case. And so one natural question is, it seems that it doesn't help, it doesn't necessarily help the user welfare to have the platform setting the price by the privacy by themselves. Can we somehow help them? So I'm going to conclude this first part of the talk by saying that one way of thinking about helping users' welfare is through regulations. For instance, one can think of GDPR as one example that almost bans data sharing, in some sense heavily impacts the connection between the second and the third layer. But as I said at the beginning of the talk, there are criticisms of GDPR that it disproportionately hurts smaller firms. For instance, this very interesting work by business econ faculty at MIT and Federal Reserve and Microsoft, which says that GDPR can be interpreted as tax, but the value of this tax is higher for smaller firms. And there are other similar findings. So what can our model say? So if we go back to our model, in our model, we have these platforms deciding on the level of noise that they add as the knob for privacy, right? So what I can say is that I can put a minimum mandate of privacy, meaning that, okay, hey, all the platforms, you should make sure that at least this level of privacy is guaranteed for the users. And if I put that minimum level equal to infinity, meaning that I fully ban data sharing, I'm going to maximize user utility only if all the platforms are low cost. So banning data sharing is optimal only if all the platforms are going to still stay at the market after banning the data sharing. This is not necessarily the case, though, if you have a market mix of, high cost and low cost platforms. And so in that case, we show that it's better to go with a minimum uniform mandate, meaning that, okay, I don't want you to fully ban data sharing, but I want to make sure that you offer a minimum level of privacy guarantee. This way, still, all these platforms are going to still stay in the market. The user enjoys the service of all of them. The competition still benefits the user, but they have made sure that they have limited the privacy leakage by putting a minimum privacy requirement. And this is better for users compared to, let's say, the case that they fully ban data sharing and some of the platforms leave the market. Of course, you would potentially benefit to go with a non-uniform privacy mandate, but there might be some practicality questions around, treating different platforms differently. But what I'm saying is that even a minimum uniform mandate could be better than full ban of data sharing in the case that you have a mixed market of, high cost and low cost. So this is just one idea of privacy regulation, kind of connects with GDPR and discussions around privacy and, differential privacy. But let me stop here and go to the second part of the talk. But maybe if there is any question about the first part, if not, I will move to the second.
Yeah, I had one in the second bullet point, like you would still be there would be a penalization on the small businesses, right? The one that
Yes.
cannot afford like this. Yeah. So there's no way of not having a bias towards big companies.
So this is the last bullet point, the non-uniform privacy mandate, having a bias towards bigger company. So this
Ah,
is going to
okay.
be optimal, actually. This is going to be optimal to have that bias. But, one may argue that there are legal challenges in implementing that because, the treating different companies differently might be challenging. Yeah, if you can do that, that's going to be optimal. But what I'm saying is that even treating them all equally could be still better than, not doing anything or fully banning the two sides of the spectrum. But if you can treat them differently, then that's certainly optimal.
And I had one more question about like this full disclosure of the level of privacy, level of Sigma. Is it true? Does it like I do not know. I'm no expert in this field. So does it like a company behave this way? Do you have like a full truth on how much they share your data?
It depends on the company. Yeah, for some they have. For instance, for Apple, they actually, if you go search Apple differential privacy, they have this, a few page document which they say exactly so they go with epsilon differential privacy, which is equivalent to, adding noise, epsilon delta, and so you can translate that epsilon to the noise that they add. So that's doable. And then they say for this app we use epsilon equal to 4, with this app we use epsilon equal to 2, with this one we use epsilon equal to 8. So yes, so they do that. Another way that you can think about this model is that user that we were talking about could be, for instance, some company itself that is selling data to other platforms and interacting with other platforms. And so so usually in contracts you can think of, I'm selling my data only if you commit to this level of privacy. But even at the user level, some companies, tech companies especially, are already saying the level of privacy guarantee that they offer to your data.
Okay. Okay. But this and just last question. All of this like is not is more on a regulation point of view, is less on like how like do you think that like users actually react to this level of privacy that they have been proposed, or this is external, and so you are the point of view is more of a regulation point of view, therefore you're trying to fix to find a strategy in order to save users to put users first.
I would so the way that users usually react to these sort of things is by seeing how much they are losing. Okay, so let me say it this way. I think questions around how users perceive privacy, right, and value of data is a tricky question, even setting aside the strategic agent, like even like, all these companies are doing epsilon differential privacy, but do really users understand what is offered to them? So this is I would say a more fundamental question. um, I believe users understand the cost of privacy through, when you get an ad from somewhere that you didn't expect, that like you search something and the day after you see something on Facebook or Instagram, like, so that type of things exist. um but yeah, but do users necessarily know, for instance, when Apple says this app is epsilon equal to 4 differentially private? I think that's a reasonable question to ask. And I think to some extent it goes beyond even, thinking of data markets as a question without even a strategy gauges. Do users appreciate, not appreciate is not the best word, but do users have a good perception of, the value of the data and the privacy offered
Yeah.
to them?
How rational are they? Are
Yeah.
they?
So
Okay.
this is I think this is to some extent a question that by itself is debatable, and I agree that this is not exactly clear. But what I'm trying to say is that, yeah, I mean, one part of it is that you think of it from regulatory aspect, and the other part is that I think that loss of privacy is something that users realize better, right? In the sense that, when you see that an advertiser have some data from you so that they can place an ad which is very closely related to what you are thinking of without even, saying to someone, that means that there is some privacy leakage happening somewhere. And that is, I think, the main factor contributing to this growing privacy concern as well, that, hey, I didn't even tell these guys what I'm looking for a shoe, but I'm seeing ad of a shoe, right? So it means that somewhere some privacy leakage is happening.
Yeah. Thanks.
Sure. So the second part of the talk would be taking a, so this is from my PhD work, and I will try to keep it short, but I'm taking a slightly different approach. I'm really taking a step back. So what I was telling you so far was with multiple platform and a data buyer. So this work, which kind of, was an earlier work, it was really thinking of one platform with multiple user. Let's forget about data buyer. And we were thinking really about the optimal architecture for a data market, for data acquisition between the users and the platform. So, what do I mean by that? Let me get to that. But we are thinking of one platform and a bunch of users, and what should be the best way of collecting the users' data. So, let me quantify this. I'm not going to define that much of new notions, but let me set the problem. So, when one think about collecting data, a popular architecture for data market has been local architectures. What is a local architecture? It's simply saying that, hey, I have n users, each of them have their data, each of them pass their data through some mapping separately from each other, and make a private copy of their data and they share it. Right. So this is a common, for instance, Apple uses this local architecture. Right. So you are treating each user's data separately through, let's say, some mappings, and they all get shared with the platform. Now, when I tell you about architecture, I'm saying that I can replace this by any mapping of users' data, right? And I'm saying that which one would be the best in terms of the learning with the minimum leakage of privacy. So remember at the beginning, I told you there's an inherent trade-off between I want to learn from the data and, the questions of privacy. And so I'm asking, if I was allowed to play a little bit with this architecture and put any mapping, is it going to be a crazy mapping that gets the optimal trade-off, or something that it is in fact realizable? let me give you a spoiler alert, a kind of a takeaway, is that it turns out that shufflers are the key to this question, to this question, and the key for the answer. What is a shuffler? A shuffler is an intermediary agent that randomizes the order of the data. And I'm not saying I'm the one that is proposing shufflers. So shufflers have been proposed and used by like some tech companies such as Google in this encode shuffle analyze algorithm. But what I'm trying to show you here is that shufflers are really giving me the optimal architecture from that trade-off point of view. And I'm gonna show you hopefully that still might not be, this might not be. So let me review this data environment. I have n users and I have this mechanism that is any mapping that basically gets user data and gives a mapping to the platform. So remember, we're learning this data before for one user. Now I'm assuming that each user's data is that xi, which is that theta now because I have multiple users, plus some idiosyncratic noise. So everyone's data can be think of, some variance of theta plus some noise that specifies their data. So you can think of theta as, prevalence of a virus in a population. You want to learn what percentage of population have COVID, let's say. But xi has this, a specific value of each user, which shows whether that particular user is infected or not. Maybe theta is the average salary of employees in a company that they want to learn. Zi is exactly showing whether a particular employee's salary is higher or lower. So Zi distinguishes you from others. So that's your private kind of aspect of data. Theta is, the mean. And we are looking into it. So I'm putting some structure on the problem because thinking of the optimal trade-off in general is quite challenging. So I'm assuming that the platform wants to learn the common parameter, but we want to keep this Zi private, right? And we assume that theta and Zi are drawn from Gaussian noise. I put variance 1 here for simplicity. And so the question that I'm asking here is what sort of mechanism M is going to be optimal here. And so the class of mechanism as I promised earlier around shuffling that I propose are called mask shuffling mechanism. So let me define them and I will state the result of optimality. So I have n users. Each user will decide whether they are going to share their data or not with a probabilistic approach. So for instance, you get a question of do you accept cookie or not? You decide whether you accept and continue or not. So this is a probabilistic approach that you take. Then all of this data, whether shared or not shared, go through a shuffler, gets permuted, and this random permutation is given to the platform. So I call this a mask shuffle mechanism. First, each data get masked with the probability, and then they go through a shuffle. The mechanism is quite simple. Now, when I say it's optimal, what do I mean by that? So again, I'm looking into this context of mean estimation or learning the mean of data, if you think about it, theta. So how much I learn about the mean is captured through this revealed information about mean. How much I learn about the specific value of each user is captured through this revealed information about each Zi and the sum of revealed informations. So if I want to learn the mean with the minimum privacy cost, in some sense, I want to move towards the lower part of the diagram, like very low on y-axis, but I want to move toward right. And the first result that I'm telling you is that there is no really, in some sense, free lunch. You cannot get any point in this region. So this is a good region for me. Like if I could, I don't know if you see my cursor, but if you could stand here, this is lovely because I can learn a lot about theta without no privacy cost, without learning anything about the specific value of the users. So I would love to be here. But this first result is saying that this region is not feasible. So I have to be above this red line. And so the question is whether I can catch the red line. And the mask shuffle mechanism that I told you about, that I mask any user's data with some probability and I keep it with the complementary, and then I shuffle, achieves this red line. And by changing the level of masking, I basically can move through this red line. And why is that? So this is really the main idea behind shuffling that is also, as I said, used in tech companies, is that many tasks in machine learning do not depend on the order of data. You want to learn something over a data set, you really don't care which data is first. You really only need over the aggregated data. And now the shuffler allows the user's data to get lost in the crowd. You don't know which data is for each user. data of user is one of these. You don't know which one. You can still learn what you want to learn, but you get this amplification of privacy. Now, shufflers, as I said, are already used by some companies because of this amplification. In fact, actually, I guess one of the most famous papers is titled "Amplifications" by it's shuffling amplification. So it's really a boost of privacy. But is it enough or not, right? If I put this shuffler into the design of data market, is it enough, or still, I'm gonna have some things that are not gonna good for the user? So I'm gonna consider a simple setting where a shuffler is there, and the platform could decide whether they are gonna use it or not with some probability. So there's a mixed strategy from the platform. And now, what do I mean by that is that if they decide to use the shuffler, your data goes through a shuffler and gets shared, all the data with that probability. With the complementary probability, they are not going to get shuffled. And so each user decide whether they are going to share their data, and the action of the user is deciding the probability of sharing. So everyone is playing a mixed strategy. So what's the challenge here? Suppose the platform commits to full shuffling, right? Mu equal to 1. I shuffle all of your data, don't worry. Now everyone will share the data. So that's good, but that means that I cannot learn so much about the private part of your data if I were to, let's say, sell your data or something. Now, on the other hand, if I do not commit to shuffling at all, I put that mu equal to 0. Now I get to see the private part of your data as well as a platform, but you will see that I have committed to 0 shuffling, so you might end up not sharing your data that often. So the balance for me is to keep the users happy to engage with me versus, learning from your data. Now, the user utility would be, again, the gain from learning data, remember this quality of service type thing, minus the privacy loss. The expected utility of the platform is that they want to learn that data, but okay, we don't have the data buyer, but we are kind of putting a surrogate here, is that if they learn about the private part of your data, they will increase their utility. Maybe you can sell it later, or they can distinguish you for certain, discrimination or stuff like that. And so the first result that we have is characterizing the user equilibrium. So suppose the platform commits to a level of shuffling, and you're looking for the symmetric user equilibrium. And we show that, this is the quite interesting part. We show that, for any level of committing to the shuffling probability, so remember, mu was the platform's commitment to shuffling, the probability of sharing would be some constant over n. So what does it mean? It means that, the more the number of users are, in probability, I'm less likely to share because I'm like, okay, there are other people that are sharing, and you will learn about this common probability. But now this constant that governs satisfies this equation. What does it mean is that the increase in mu will lead to an increase in the solution of this. So it means that if you offer better and better shuffling, I will increase my probability of sharing. I will be more happier with the privacy guarantee, so I will increase my probability of shuffling. And at the case that you offer full shuffling, I will get to, a constant probability of sharing. So that mu increases to the point that C increases to the point that is comparable with N. And in some sense, if I offer full shuffling, you will share your data with me with a constant probability. Which kind of makes sense. Like my data is almost getting lost in the crowd, so I'm happy to share my data. And now for any level of mu, there is a corresponding probability of sharing that I told about you. So a Stackelberg equilibrium would be that I, as a platform, think that, for any level of mu, this is the corresponding probability. I pick the probability of shuffling, the one that maximizes, combined with this best response maximizes my utility. So this is going to be very similar in terms of the notion of equilibrium to the first part. And so the result that we have, so I'm going to show two results and I'm going to stop. The first one is that in terms of the characterization of the optimal shuffling, I will look at how much users care about learning this data. So remember, users want to learn this common parameter, the parameter that we are setting all the game to learn. And if they do not care that much, right? If users are not that much in need of the service, what they are going to do is that the platform has to offer full shuffling to persuade them to share their data. On the other hand, if users care too much about learning data, then the platform has to, can get away with offering no shuffling and still you're going to share your data. Suppose I'm doing a cancer drug research and you really want to know whether this drug is effective or not. You really need to know that. So I can get away with violating, in some sense, privacy and exploiting the privacy and not offering any shuffling, and you're going to still share your data. And in between, this is going to be a transitory phase. Now, everything seems reasonable. This is an expected result. The more you need the data, the more I can get away with the privacy leakage or exploiting your data. So one last question that I ask is that does this in this transitory phase, the more that you need the data, does it mean that at least your utility increases? It kind of makes sense, right? The more that you need to data, at least when you learn it, you're going to be happier, right? So does it mean that that's the case? Or maybe the equilibrium changes and the privacy exploiting changes, the exploitation of your privacy changes to the point that your total utility could go down. Despite the fact that you're enjoying a better service, your privacy loss increases to the point that your total utility go down. And this, in fact, is the case. We show that as your need for the data increases, remember this gamma was how much you need to learn that common parameter. There is a point that your total utility could go down. Why is that? Again, I will show you in a second. But the reason basically is that the privacy cost now is going to increase and I'm going to offset all the gain that you get from learning this common parameter. So remember this figure. Look at this case. If I increase gamma, yes, you're happy, but I start to offering you lower privacy. So your privacy cost jumps up because the shuffling goes down. But at the same time, you learn more and more about data, and the total combination ends up hurting. So we have further so all of this shows that the privacy guarantee that is offered to you is to some extent fragile to this monopoly of the platform here. We have the shuffling. Shuffling seems to be good, but it's still not good enough to protect you when you are in need of the service of the platform. We have additional results on what is the optimal choice of mechanism from platform's point of view. I'm going to jump on that. And I'm going to mainly end the talk with two set of takeaways. I know a lot of notations and theory, but two set of takeaways. The first one is that competition by itself from the first part of the talk does not improve the user. However, regulations combined with competition could be good for users. And the optimal regulation is not necessarily the immediate one, such as banning data sharing. It could be more nuanced there. For the second one, what I'm trying to say is that shuffling procedure is a very good one in terms of offering a privacy guarantee for users. In fact, if you think more broadly about it, design of the data market by itself could help the users. But in the presence of a monopolist platform, it's not again enough by itself, especially if users are in need of the service of the platform. If the platform has a monopoly, users are in need of its service, it's not again enough. And one result that they didn't show you is that all of this shuffling is something that is good from users' point of view. It's not necessarily the optimal from platform's point of view. And so the decision of whether using or not at the first place is a platform's decision. And if it's up to them, they do not necessarily use it. So that's another debate of how to persuade platforms to use certain things that are optimal from users' point of view, but not from their point of view. With that, let me stop here and thank you.
Thank you very much. So we had already some questions, especially on the first work. Are there more questions?
Stop.
So I have some naive question about the second work. You said that there are uh, a lot of like the task that you want to perform are symmetric with respect to the population. So since I come from infill games, this would be that basically I am interested in the distribution of the people and not really into the label of the people itself. And so is there something that has been like somehow experienced, proven, like empirically, or like is there something that is a common knowledge in the literature?
You mean in
I don't
terms
know
of
if
shuffling?
Yeah, if you, even the term, or like, is there you said that a lot of so usually the parameter you're interested in is something that is invariant with respect to shuffling, right? And why is that? Why
Oh,
is
I
there
see, I
like
see.
a
So, yeah, many cases of the serv. So, yeah, so there is a. Okay, that's a good question. So, if you want to offer a personalized recommendation to someone, then that doesn't work, right? But suppose that, for instance, Apple is trying to learn some large language model that predicts, the next word of, the text message that you're typing, right? So
Mhm.
this doesn't necessarily, so it gets the input as your current sentence, but training this model by itself doesn't necessarily need to know whose text I'm feeding to, right? So
Yeah.
I can feed all the data set of text messages into it and train it. Or I don't know, suppose I'm training some image classifier. So this is cat, label of cat, dog, label of dog. I can collect all these images and feed it. I really don't need to know which the subset of images are coming from which user. So yes, so in this many settings, the data set by itself doesn't need to be in any order. It's an aggregated set of data. If you change the order of the data set, nothing changes. So in all those examples, you can use shuffling, and that's actually even, I mean, setting aside the data markets with non-strategic users is something that is used and analyzed in differential privacy literature. But, and as I said, it's not something that I invented, is there. But yeah, but if you want to have a specific user, specific model, then yeah, shuffling is not gonna work.
Yeah, no, I understand. And I had one more question. Can you go back to your slides to where
Okay.
there was a moment in the second part where you said that you did a special relationship between even before there was a special relationship between
Oh, this one.
yes, that one. Yeah. Can you give more intuition on this one? Why would you want this kind of relationship?
Oh, I
What
see. So I
why
want to characterize the equilibrium, right? So I say
yeah,
that for any level of platform's action mu. So what is platform action? So the platform says, okay, I'm going to shuffle your data with this probability mu, right?
yeah,
So let me go to this figure. So suppose the platform says that I'm going to use this shuffler with some probability mu, right?
yeah.
Now, as a user, you may decide whether you share your data or not. So there's a mixed strategy. And this probability of you deciding to do it or not is denoted by Q.
Mm-hmm.
So intuitively, the higher mu is, it means that I'm offering you a better privacy guarantee. This Q will be also higher, right? I'm more willing to share my data because in some sense, shuffler is used more often. So now this the result is saying that when the relation, so for fixed mu, the q is some constant over n. So over n is because there are n users. So I think that if I share my data less often, there are still other people that are sharing. Is everything is going to be learned. So I'm getting some free ride in some sense. So I'm
Yeah.
sharing c over n. But now that c is the answer to this equation, and you can show that the solution to this is increasing as a function of mu. So the higher the mu is, the higher the solution will be, C will be. So this is really the intuition that I was telling you. The higher mu is, the higher probability of shuffling is, I'm more likely to share, and that shows itself in this C. And I need this characterization because I want to characterize the equilibrium and then study, what's the optimal mu, as is that. And so the further results that I showed you about the properties of the equilibrium.
Yeah. Okay. Thank you. So, okay, if there are no more questions, let's thank Alireza again. And thank you everyone for connecting. And see you in 1 month for the next session of Surfing the Ocean. Bye. Bye bye.
Bye.